Good morning, everybody. Can you hear me?
Good morning, sir.
So, we'll continue with the same topic, that is evaluation of state transition matrix. We've already discussed two methods of evaluating the state transition matrix. One is using Laplace transform method. And second method that we discussed yesterday was using Cayley-Hamilton theorem. Is it okay? So these two methods we have already discussed. Today we will be discussing the third method of evaluating the state transition matrix, that is using similarity transformation. This is the third method of evaluation of state transition matrix that we will be discussing. Basically, our problem is that given A, जो हम problem actually solve कर रहे हैं, that is given a square matrix A of order n, evaluate e to the power at. This is the problem that we are discussing. And we have already talked about two methods of evaluating it, and the third method we'll be discussing, that is using similarity transformation. Similarity transformation I have already discussed with you. Now we will see how we can use it to evaluate this state transition matrix. Before I start with this method, actual method, I would like to give you some background knowledge about this method, or the what you call the tools that will require to implement this method. First of all, we'll start with the notion of eigenvalues and eigenvectors once again. I'm revisiting this. Eigenvalues and eigenvectors. Now, so far you know that given a matrix A, you can evaluate its eigenvalues by solving its characteristic equation. I would like to give you a geometrical interpretation of the same thing, the eigenvalue, because I would require this in the method that we are going to discuss. If you have an n-dimensional space, and on the blackboard I can show you only two-dimensional space. Let's say this is x1 and this is x2, and any vector in this space is represented by means of a point, or we can show it as a line whose length actually is the magnitude of this vector, and it also has direction associated with it. Every vector has got a magnitude as well as direction. So the direction is really measured in terms of the angle that it makes with the positive x-axis. Now, if you do some, so let's call this vector as x. It has two components, x1 and x, for a two-dimensional space. So let us say this vector is something like this, 2 and 4. So let's say this is x. If you perform an operation ax on this vector, where A is a matrix of size 2 cross 2, if I do something like this, A is any matrix, let's say 1, 2, 1 and 5 as an example, and you multiply this matrix with this vector 2, 4, what do you get? You actually get this 1, 2, 2, 2 plus 4 means 8, 2 into 4 means 8, that means you get 10 here, and 2 plus 20 is 22. So you get another vector in the same space. The size of this matrix is 2 cross 2, and the size of this vector is 2 cross 1. When you multiply them, you get another vector of the same dimension, that is 2 cross 1. That means you actually have performed the operation AX, and you have ended up with another vector Y in the same space. Let's call this vector as Y. So this vector Y has got a magnitude associated with it, as well as the direction. So this vector can also be represented by in this two-dimensional space by another vector like this. Are you getting me? So when you perform this operation, which is actually known as, this is a linear transformation performed on X, because you see this matrix, when you multiply it with this, the entries of this vector are actually changed through a linear combination, because this 10 is actually equal to 1 into 2 plus 2 into 4. That means ये वाला वेक्टर है, इसकी जो एंट्रीज हैं, they are actually the entries of the new vector, actually the linear combinations of the original vector, और linear combination के लिए जो coefficients produce करता है वो ये matrix provide करता है. जैसे ये वाला column जो है इसका, it is actually linearly combined with these entries, and you end up with this entry, and similarly you end up with this entry. So this is known as this we call as, this is a linear operation. And matrix A is said to be a linear operator. So we have seen here that when we perform this operation on this vector, we pre-multiply it by a matrix A, you end up with another vector which actually has got a change in magnitude as well as a change in direction. आपको एक different vector मिल जाता है यहाँ पे. We call this as X and we can call this as Y. But sometimes if you do the same operation on some special vectors, like if I consider if V is a vector which is a special vector. Why do I call it a special vector? Because when I do the same operation on this vector, that is when I pre-multiply this V by a matrix A, I end up with another vector, let's say U, which is actually a scaled version of the same vector. ये V की स्पेशलिटी क्या है? V की स्पेशलिटी ये है कि जब इसको प्री-मल्टीप्लाई करते हैं एक मैट्रिक्स A से, और इस मैट्रिक्स A और इस V में एक रिलेशन है आपस में, and when I pre-multiply it by this matrix A, I end up with another vector as I do in this case also, but that particular vector may have a different magnitude as compared to the original vector, but it is in the same direction as that of the original vector. जैसे आप यहाँ lambda is a scalar actually. Lambda is a scalar. That means when I am pre-multiplying this vector V by matrix A, let's say you have got A and V. V vector is a vector of dimension n cross 1. This is a matrix of dimension n cross n. When I multiply them, I'll naturally end up in another vector U, which will also be of dimension n cross 1. But V is a special vector in the sense that when I'm pre-multiplying it by a specific A, I am ending up with another vector because I am multiplying a matrix by a vector and that particular vector is actually a scaled version of this vector. It actually has the same direction as the original vector. Normally what happens is, for any non-special vector, when you will pre-multiply it by a matrix A, you will end up with another vector which will have the changed magnitude as well as changed direction. But this is a special vector in the sense that when I pre-multiply it by a specific matrix A, I am ending up with another vector U, which actually is a scaled version of the same vector. These special vectors are known as the eigenvectors of A. These special vectors are known as eigenvectors of A. And lambda is the corresponding eigenvalue, scaling factor. Lambda is the corresponding eigenvalue. Do you get me? Is that clear? So I will sum it up like this. For any square matrix of square matrix A of order n is a square matrix, there will be n special vectors known as eigenvectors which satisfy the following relation. That is A V I, because there will be n such vectors, that will be equal to lambda I V I, where I runs from 1 to n, Vi are the eigenvectors. It's like basically the ith eigenvector. I running from 1 to n, and lambda I are the corresponding eigenvalues. I running from 1, 2, 3, so on. So that means you, for any n cross n matrix of n cross n this matrix, you will have the following relationships: A V1 equal to lambda 1 V1. This is the first eigenvector, and this is the corresponding eigenvalue, the scaling factor. That means when you multiply this V1 by when you multiply pre-multiply this V1 by matrix A, जिसका ये eigenvector है, you will end up with another vector in the same direction. It's like this. You have a vector here. If it is an eigenvector and you multiply it by matrix A, जिसका ये eigenvector है, you will end up with another vector in the same direction. It is a different magnitude, but the direction is same. And the scaling factor, the factor by which this magnitude changes, that is known as the eigenvalue. Is that clear? Is that clear to you?
Yes, sir.
Okay. तो ऐसे ही जैसे अगर आपके पास nth ऑर्डर का मैट्रिक्स है, आपके पास n ऐसी रिलेशंस होंगी. A v1 equal to lambda 1 v1, A v2 equal to lambda 2 v2, so on. A v n minus 1 equal to lambda n minus 1 v n minus 1. अभी मैं एक ऐसा केस ले रहा हूँ जिसमें कि आइगन वैल्यूज डिस्टिंक्ट हैं. आपको पता है कि कुछ केसेस में आइगन वैल्यूज नॉन डिस्टिंक्ट भी होते हैं. So I am taking the case wherein the eigenvalues are distinct. So another one will be A v n equal to lambda n v n. ऐसे आपको रिलेशनशिप्स मिलेंगी जो कि मैंने सम अप की थी ऐसे a vi equal to lambda I b. I can even write it in compact form as lambda I minus a into vi is equal to 0. Is that okay? तो ये जो आप बेसिकली solve करते हो when you say that we have to solve the determinant of this equation in order to get the eigenvalues, this is where this expression lambda I a minus I comes from. जो आप determinant of lambda I minus a लेके characteristic equation solve करते हो, this actually comes from this. So I'll come back to that. Eigenvalues का जो solution है मैं वापस आऊँगा उस पर. So this basically is the expression which actually shows the relationship between the eigenvalues and the corresponding eigenvectors and the corresponding eigenvalues. Is that clear? Mind it, this is a vector. These are eigenvectors. So these are n components. So if I come back to this expression AVI equal to lambda I VI, AVI equal to lambda I VI, और इसकी जो मैंने बहुत सारी एक्सप्रेशंस लिखी जो मैंने अलग अलग लिखा है इक्वेशंस को AV1 equal to lambda 1 V1 I'm rewriting it AV2 equal to lambda 2 V2 and so on AVN equal to lambda n Vn. If I express these equations in matrix form, expressing these n equations in matrix form, I can write so this is A, then this is V1, V2, so on up to Vn is equal to V1, V2, so on up to Vn lambda 1 0 0 so on up to 0 0 lambda 2 0 so on up to 0 0 0 so on lambda n minus 1 0 and 0 0 0 so on 0 lambda n. Please understand this properly. So basically what you have, this V1 is a vector, it's a column vector, first eigenvector. इसके n components होंगे, V1 के n components होंगे, V2 के भी n components होंगे, Vn के भी n components होंगे. ये actually matrix है, it's a matrix having matrix having eigenvectors as its columns. ये जो मैं यहाँ पे ये दिखा रहा हूँ ये V1, V2, Vn. Can anybody tell me what will be the size of this matrix? V1 जो eigenvector है, it is actually like this. V11, V12, so on, V1n. ये vector है ना basically. Are you getting me?
Yes, sir.
ये बेसिकली वेक्टर है. तो ये जो मैट्रिक्स मैंने यहाँ पे दिखाया इसका साइज क्या होगा? Yes, tell me what will be the size of this?
N cross n.
Yes?
N cross n.
N cross n, isn't it? Because basically these are all vectors, n cross 1 vectors. तो ये जो मैंने इसको मैट्रिक्स फॉर्म में लिखा, it actually should satisfy these relationships. AV1 equal to lambda 1 V1. तो यहाँ पे अगर मैं ये A अंदर लेके जाऊँ, so this is AV1. As you can see here, V1 के जो सभी एंट्रीज होंगी, these will get scaled by lambda 1, isn't it? See, अगर मैं ये V1 खोल के लिखूं, so this will be V11, V12, so on up to V1n. isn't it? मेरा expression क्या है? A V1 equal to lambda 1 V1. So you can see here, when we do the matrix multiplication, V11 will get multiplied by lambda 1, isn't it? जब मैं मैट्रिक्स मल्टीप्लिकेशन यहाँ पे करूंगा तो V11 खाली जो पहले वाले वेक्टर की जो एंट्रीज हैं, इसकी जो कॉलम की एंट्रीज हैं, they will get scaled by lambda 1. When you will perform this matrix multiplication, actually the first column will be what? The first column will be lambda 1 V11. Sorry, lambda 1 V1, because this will be lambda 1 V11. Then you will when you will perform this matrix multiplication of second row with this column, so V12 will get multiplied by lambda 1. So इस particular column की सभी entries scale हो जाएंगी lambda 1 से. Please try to understand this properly. Basically मेरा जो relation है, that is A1 is equal to lambda 1 V1. तो उसी को मैंने matrix form में लिखा. तो ये जो matrix form में लिखा ये correspond करना चाहिए ना इसके साथ. Left hand side तो okay है. तो A V1 पहली वाली entry बनेगी इसकी. और यहाँ से पहली वाली entry क्या बनेगी when you perform the matrix multiplication? That will be the first particular vector, that is V1 जिसको हमने कहा है, और जिसकी n entries हैं, वो सभी entries scale हो जाएंगी with lambda 1. सेकेंड वाले कॉलम की सभी एंट्रीज स्केल हो जाएंगी विद लैम्डा 2, और इसी तरह लास्ट वाले वेक्टर की सभी एंट्रीज स्केल हो जाएंगी विद लैम्डा n. इज दैट ओके? और शैल आई एक्सप्लेन इट वंस अगेन? जस्ट टेल मी. हाँ जी, yes, tell me.
Okay, sir. Okay.
Sir, आया समझ.
So you understood it. So if I call this matrix as P, so this is also P, and this I call as capital lambda, like this. So I can write this expression as A P is equal to P into lambda, isn't it? Where P क्या है? P is a matrix having the eigenvectors of A as its columns, isn't it? तो P वाला जो मैट्रिक्स बना वो कैसे बना? मैंने आइगन वेक्टर्स स्टैक कर लिए इस मैट्रिक्स में as the columns of a particular matrix which I am calling as P. और ये जो लैम्डा है, it's a diagonal matrix. Lambda 1 0 0 so on up to 0, then 0 lambda 2 so 0 up to 0 0 0 0 lambda n. और उसकी डायगोनल पे क्या है? इस मैट्रिक्स लैम्डा की डायगोनल पे आइगन वैल्यूज हैं. You can see here along the diagonal, it's a diagonal matrix basically. And as you have already seen, this is a matrix in Jordan's canonical form because it has got along the diagonal the eigenvalues of the matrix A. Is that clear? So this is a matrix in Jordan's canonical form. This is a matrix in Jordan's canonical form. So that means I have got A, P equal to P and lambda. Assuming P to be an invertible matrix, I'll prove it later on that P is actually an invertible matrix. That means ये जो matrix बना इसकी की columns eigenvectors हैं, I'm assuming it to be an invertible matrix. We'll prove it later on. In today's lecture only, if you'll get the time, we'll be proving it. For the time being, I'm assuming it. We'll prove it later on. Assuming P to be an invertible matrix, I can pre-multiply this equation 1 by P inverse. We can pre-multiply equation 1 by P inverse. So we can get P inverse of AP is equal to this matrix. Is that okay? So if P is an invertible matrix, I can pre-multiply this equation 1 by P inverse and I end up with this thing. Is that clear? A is a non-diagonal matrix. I am converting it into an equivalent diagonal matrix by performing this operation, P inverse of AP. So P inverse of AP or PAP inverse, we have already seen that that is an operation that we do in similarity transformations. So here you can say that this A and this matrix lambda are similar matrices. What do we mean by similar matrices? That is, they can be obtained by similarity transformation. इसका मतलब ये हुआ कि अगर आपको कोई एक मैट्रिक्स दिया गया है ए और आपको कहा जा रहा है कि इसको डायगोनलाइज करो, तो आप कैसे करोगे? आप इसके आइगन वेक्टर्स ऑब्टेन करोगे। मैट्रिक्स ए के आप आइगन वेक्टर्स ऑब्टेन करोगे, उसको एक मैट्रिक्स में डालोगे जिसका नाम आप पी रखोगे, एंड देन यू परफॉर्म दिस ऑपरेशन पी इनवर्स ऑफ एपी, इट्स गोइंग टू डायगोनलाइज इट। और इसमें हमने एक assumption ली कि पी वाला मैट्रिक्स जो है ये इन्वर्टिबल मैट्रिक्स है, क्योंकि तभी हम ये ऑपरेशन परफॉर्म कर पाएंगे। और पी के इन्वर्टिबल होने के लिए जरूरी है कि ये जो आइगन वेक्टर्स वाला मैट्रिक्स बना, ये वाला मैट्रिक्स पी एक्चुअली इज दिस मैट्रिक्स, so we are saying that this has to be invertible if we want to perform this operation. तो इसकी इन्वर्टिबिलिटी हम प्रूव करेंगे कि ये इन्वर्टिबल होता है कि नहीं है। उसके इन्वर्टिबल के लिए हमें ये प्रूव करना पड़ेगा कि ये जो आइगन वेक्टर्स हैं they are actually linearly independent. So we are going to prove this. Is it clear up till now? Yes.
Yes, sir.
Okay. So this relationship actually we are going to use. अभी ये पेंडिंग है, हमें ये प्रूव करना है कि P इन्वर्टिबल मैट्रिक्स है। और इस केस में हमने एक और assumption ये ली थी कि आइगन वैल्यूज डिस्टिंक्ट हैं, because I have taken separate eigen values lambda 1 lambda 2 up to lambda n. So in case the eigen values are distinct, we can actually evaluate the state transition matrix by actually using this relationship. तो अब हम फिर से अपनी प्रॉब्लम पे फिर से लौट के आते हैं। हमारा प्रॉब्लम बेसिकली था, we actually had to evaluate the state transition matrix. We'll come back to that. So we are actually trying to evaluate e to the power 80, isn't it? e to the power 80 हम evaluate करने की कोशिश कर रहे हैं। तो e to the power 80 को evaluate करने के लिए हम क्या करेंगे? Basically, we'll do something like this. So basically, the method that we are using is using similarity transformation. यही similarity transformation जो अभी मैंने यहाँ पे आपको define की, किसी भी matrix को diagonalize करने के लिए। Only thing is that we are assume that A has distinct eigenvalues. Lambda 1, lambda 2, so on, up to lambda n. And let V1, V2, so on, Vn be the associated eigenvectors. Then we have already proved that e to the power, we already proved that A and lambda, or A can be diagonalized to the operation A is equal to, sorry, P inverse of AP equal to 1. So this operation actually we are going to use in order to evaluate the state transition matrix. तो इसको हम कैसे यूज करेंगे स्टेट ट्रांजिशन मैट्रिक्स को इवैल्यूएट करने के लिए, लेट्स सी. So you have got, consider P inverse of e to the power ATP. E to the power AT is the state transition matrix. I am considering this expression. So this is P inverse of, what is e to the power AT equal to? This is I plus AT plus a square t square upon 2 factorial plus 1 into P, which is actually equal to, so if I just take this P inverse and P inside, so I have got P inverse P plus P inverse APP plus P inverse A square P T square upon 2 factorial. P or T square को मैं I can interchange because T is a scalar plus 1. So I can write it as, so this is P inverse P is I and P inverse AP, what is this equal to? That's equal to lambda. So this is lambda T, isn't it? Then I have this thing I can write as P inverse, this is A square है ना यहाँ पे ये, I can write it as A into A, then P T square upon 2 factorial into T square, sorry, plus 1. So that is I plus lambda T plus P inverse of A, and here I can insert P inverse. Then I have AP T square upon 2 factorial plus 1. यहाँ पे बीच में मैंने ये PP inverse insert कर लिया, तो PP inverse because it's equal to I, so this is not going to change the things. Is that okay? Are you following
Yes.
me?
Yes, sir. Yes, sir.
So now this P inverse of AP, it is lambda, and this P inverse of AP, this is also lambda. So this makes it lambda square. So we get I plus lambda T plus lambda into lambda. This is lambda square T square upon 2 factorial plus 1. Is that okay?
Yes, sir.
Okay. So that's actually equal to, what is that equal to? That's e to the power lambda T, by definition of state transition matrix. So what we have seen is, so which implies what we have proved is that P inverse of e to the power AT into P, that is e to the power lambda T. Is that okay? And which in turn implies that e to the power AT and e to the power lambda T are similar matrices. What do you mean by similar matrices? That is, they can be obtained from each other by similarity transformation. इसका मतलब है मुझे एक्चुअली ये जो e to the power AT और e to the power lambda t है, इसको आप इवैल्यूएट इसको आप ऑब्टेन कर सकते हो बाय मींस ऑफ सिमिलैरिटी ट्रांसफॉर्मेशन. और सिमिलैरिटी ट्रांसफॉर्मेशन के लिए जो मैट्रिक्स यूज करोगे वो वही p होगा जिससे a लैम्डा में चेंज हो गया था. इट इज सेम p. द p that is obtained by stacking the eigenvectors of matrix A together as the columns of a matrix P. Is that clear? Now, how is it going to help me in evaluating e to the power 80? I basically have to evaluate e to the power 80, isn't it? तो ये मुझे कैसे help करेगा e to the power 80 easily evaluate करने में? Let's see. Now, I have the expression P inverse of e to the power 80 into P is e to the power lambda t. So if I pre-multiply by P and post-multiply by P inverse, I'll get e to the power, I'll get P e to the power lambda t, P inverse is equal to e to the power 80. Is that okay? अभी जो मैंने assumption लिया था कि P एक invertible matrix में उसको यूज करता जा रहा हूँ, मैंने प्रूव नहीं किया अभी कि P invertible matrix. I am going to do it later on. तो फिलहाल मैं ये assumption लेके जा रहा हूँ कि P एक invertible matrix है. तो अगर मैं इसमें इस एक्सप्रेशन को प्री मल्टीप्लाई करूं P से और पोस्ट मल्टीप्लाई करूं P इनवर्स से, आई विल गेट e to the power 80 equal to P e to the power lambda t into P inverse. Is that okay? Is that clear to you?
सर आपने वो क्या किया, प्री मल्टीप्लाई किससे किया?
प्री मल्टीप्लाई मैंने P से किया, तो यहाँ पे भी P आएगा ना?
यस सर.
और पोस्ट मल्टीप्लाई P इनवर्स से किया, तो ये PP इनवर्स I हो गया, ये PP इनवर्स I हो गया.
यस सर, यस सर.
So I get e to the power 80 equal to P e to the power lambda t into P inverse. Is that okay?
यस सर.
तो ये वाले एक्सप्रेशन में यूज करूंगा e to the power 80 को इवैल्यूएट करने के लिए. तो कैसे करेंगे? See how I am going to use this expression. If, as I have already written, lambda 1, lambda 2, lambda n are the eigenvalues associated with this matrix, eigenvectors, eigenvalues associated with this matrix A. और आपको पता है lambda जो है, lambda क्या है? Lambda है lambda 1 0 so on up to 0, then 0 lambda 2 so on up to 0, then like this 0 0 so on lambda n minus 1, lambda n minus 1 will be here, then 0 0 so on 0 into lambda n. ये आपका lambda है ना? डायगोनल मैट्रिक्स है, जो मैंने स्टार्ट में भी कहा था कि डायगोनल मैट्रिक्स एक बहुत ही ब्यूटीफुल मैट्रिक्स है, इसकी बहुत ही स्पेशल प्रॉपर्टीज होती हैं. जैसे I had talked when I was discussing the canonical matrices with you, I told you that diagonal matrix is one of the very special canonical matrices. और उस समय मैंने ये भी मेंशन किया था कि अगर आपको इसका इनवर्स ऑब्टेन करना है, तो इसके इन्वर्शन के लिए आपको जस्ट इन एंट्रीज
1 upon lambda 1.
है ना?
यस सर.
1 upon lambda 1, so it becomes easy. Similarly, this operation e to the power lambda t on this matrix, it will become a trivial task. You just have to perform it individually on these eigenvalues. So it will be like this: e to the power lambda 1 t so on up to 0, 0 e to the power lambda 2 t so on up to 0, then like this 0 0 so on e to the power lambda n minus 1 t and 0. Are you following me? Then 0 0 so on e to the power lambda n. Is that okay? मुझे अगर एक डायगोनल मैट्रिक्स दिया गया है और उसका मुझे स्टेट ट्रांजिशन मैट्रिक्स e to the power lambda t इवैल्यूएट करना है, तो I just have to take this expression is to be तो ये स्केलर ऑपरेशन मुझे परफॉर्म करने हैं on each eigenvalue. I can do it simply like this: e to the power lambda 1 t e to the power lambda t so on up to e to the power lambda n t. So it becomes an easy task for a diagonal matrix. लेकिन मेरा जो एक्चुअल प्रॉब्लम है, I have to obtain e to the power 80. And what's e to the power 80 equal to? We have already seen it. It's p e to the power lambda t into p inverse. So it's p e to the power lambda t into p inverse. तो बस p को obtain करो, p inverse भी obtain करो, और इस एक्सप्रेशन से आप e to the power 80 वैल्यू कर सकते हो. Is that okay? Is that clear? मेरा जो एक्चुअल प्रॉब्लम था, मैंने किसी भी मैट्रिक्स A के लिए e to the power 80 इवैल्यूएट करना था. e to the power 80 इवैल्यूएट करने में प्रॉब्लम हो रहा था, तो e to the power 80 को इवैल्यूएट करने के लिए मैं ये वाली एक्सप्रेशन यूज कर सकता हूँ, क्योंकि e to the power lambda t इवैल्यूएट करना इजी है, बिकॉज इट्स अ डायगोनल मैट्रिक्स. डायगोनल मैट्रिक्स के लिए e to the power lambda t इवैल्यूएट करना, इट इज सिंपली बाय टेकिंग द एक्सपोनेंशियल ऑफ each eigenvalue e to the power lambda 1 t lambda 2 t so on up to lambda n t, So P, and only problem that remains here is that you have to compute the matrix P. And what is the matrix P? Matrix P is the matrix of whose columns are the eigenvectors of matrix A. अब इसमें जो प्रॉब्लम रहती है कि आइगन वेक्टर्स को कैसे इवैल्यूएट किया जाए, तो हम देखेंगे आइगन वेक्टर्स को इवैल्यूएट कैसे करते हैं. Have you understood this?
Yes, sir.
So this is your third method for evaluating the state transition matrix. हमने तीन मेथड्स देखे स्टेट ट्रांजिशन, लेकिन इसमें एक रेस्ट्रिक्शन ये है कि आपका जो मैट्रिक्स ए है इसके आइगन वैल्यूज डिस्टिंक्ट होने चाहिए, क्योंकि हमने देखा है जब हमने रियलाइजेशन प्रॉब्लम डिस्कस की थी जॉर्डन्स कैनोनिकल फॉर्म की, उसमें भी हमने देखा था कि प्योर डायगोनल फॉर्म जो रिप्रेजेंटेशन आती है वो खाली उस केस के लिए आती है जहां पे कि आइगन वैल्यूज डिस्टिंक्ट हो. अगर आइगन वैल्यूज नॉन डिस्टिंक्ट हो, जो कि आपको मैंने असाइनमेंट दिया था, उसमें आपने देखा था कि जॉर्डन्स ब्लॉक्स बनते हैं, उसमें प्योर डायगोनल फॉर्म रिप्रेजेंटेशन नहीं आती. Isn't it? If you have done that assignment sincerely, you would have already seen that pure diagonal form representation is not possible for a matrix which has got non-distinct eigenvalues. For a matrix A which has distinct eigenvalues, you can use this particular expression for evaluating the state transition. Is that okay?
Yes, sir.
Okay. So these are the three methods used for evaluating state transition. Now, before we show you some numericals on that, I would like to first of all go back to that problem जो मैंने अभी कहा था कि P एक invertible matrix है, ये हमने प्रूव करना है कि किसी भी मैट्रिक्स A के अगर ये आइगन वेक्टर्स हैं और अगर उसके corresponding आइगन वैल्यूज डिस्टिंक्ट हैं given by lambda 1 lambda 2 up to lambda n, then actually this matrix P that which you form by stacking the eigen vectors together as its columns, this matrix A P we have to prove that it is an invertible matrix. Is that clear? So we will prove, and I'll be stating a theorem जिसमें कि हम ये चीज प्रूव करेंगे. I'll give you statement of the theorem and then we'll prove it. So if we have, let V1, V2, so on up to Vn be the eigenvectors associated with distinct eigenvalues lambda 1, lambda 2, so on up to lambda n of a square matrix A. Then the vectors V1, V2, so on up to Vn are linearly independent. That's another way of saying that matrix P is an invertible matrix. We have to prove that the vectors V1, the theorem states that the vectors V1, V2 up to Vn are linearly independent, and the matrix P defined as P is equal to V1, V2, so on up to Vn transforms A into Jordan's canonical. दूसरा वाला हिस्सा हमने इसका प्रूव ऑलरेडी कर लिया. ये मैट्रिक्स P किसी भी मैट्रिक्स A को जॉर्डन्स कैनोनिकल फॉर्म में ट्रांसफॉर्म करता है बाय सिमिलैरिटी ट्रांसफॉर्मेशन. लेकिन उसमें हमें assumption ये ली थी कि P इन्वर्टिबल मैट्रिक्स है, वो हम अब प्रूव करेंगे कि ये जो P मैट्रिक्स है जिसके कॉलम्स आइगन वेक्टर्स हैं मैट्रिक्स A के, this is an invertible matrix, and another way of saying the same thing is that the columns of this matrix P are linearly independent. Do you understand? I had already talked a bit about linear dependence and independence of vectors. When are the vectors said to be linearly independent? If you have two vectors, 1, 2 and 2, 4, ये दो वेक्टर्स हैं, ये v1 है, ये v2 है। ये दो वेक्टर्स लीनियरली डिपेंडेंट हैं या इंडिपेंडेंट हैं? यस। Are these two vectors linearly dependent or independent? I'm waiting for your answer.
Dependent.
Why are these dependent vectors?
Dependent.
Yes. क्यों है डिपेंडेंट ये?
सर V1 एंड V2 कैन बी, मतलब उसमें एक रिलेशन आ जाता है, लाइक V2 is to V1 बोल के।
Because actually v2 is equal to 2 times v1, isn't it? That is, v2 can be obtained from v1 by a simple linear operation. They are linearly related. They are linearly dependent on each other. ये graphically अगर आप देखो इन दो vectors का same direction होगा, isn't it? और अगर आप इस matrix का, will this matrix be invertible or non-invertible? ये जो मैट्रिक्स है ये इन्वर्टिबल मैट्रिक्स है या नॉन इन्वर्टिबल मैट्रिक्स है?
नॉन इन्वर्टिबल सर, डिटर्मिनेंट।
नॉन इन्वर्टिबल क्यों है?
डिटर्मिनेंट सर इसका जी।
क्योंकि इसका डिटर्मिनेंट 0 आएगा, है ना? तो किसी भी
Yes.
मैट्रिक्स की इन्वर्टिबिलिटी के लिए जरूरी है कि इसके जो कॉलम्स हैं या रोज, वो एक ही बात है, इसके जो कॉलम्स हैं वो लीनियरली इंडिपेंडेंट होने चाहिए, isn't it? अगर वो लीनियरली डिपेंडेंट हुए तो उस केस में ये मैट्रिक्स इन्वर्टिबल नहीं रहता। तो किसी भी मैट्रिसेस की इन्वर्टिबिलिटी के लिए जरूरी है कि उसके जो कॉलम्स हैं या रोज हैं, that is the same information is contained in both of them, they should be linearly independent. Is that okay?
यस सर।
Yes. Okay. दूसरे लफ्जों में आप इसको ऐसे भी देख सकते हो, if you perform some column operations here, if I do some column operations, like if I multiply this column by 2 and then subtract it from this, that means you perform some linear operations. If I multiply column 1 by 2 and subtract it from column 2, what will I get? I'll get this as 0 0 and this as 2 4, isn't it? I have multiplied column 1 by 2 by this, let me call this as column 1 ताकि confusion हो जाए आपको, and subtract it from column 2. Is that okay? I have multiplied column 1 by 2, so this becomes 2 and 4, and I have subtracted this from this, so I get this as 0 0 and this as 2 4. So you have ended up with a row of zeros. So that also goes on to prove that this matrix is actually a rank deficient matrix and its columns are linearly dependent. Is that okay?
यस सर।
Is that okay? So what actually I have done is I have multiplied this column v1. v1 वाले कॉलम को मैंने 2 से मल्टीप्लाई किया, मैंने ये ऑपरेशन परफॉर्म किया, 2v1, और इसको फिर सब्ट्रैक्ट किया v2 के साथ, v2 को मल्टीप्लाई किया 1 से, मान लो 1 into v2, and I have ended up with a zero column. Isn't it? Is that okay?
यस सर।
Okay. So that means if I take another case like 1, 2, 2 and 5. What about these two vectors?
इंडिपेंडेंट सर, लिनियरली इंडिपेंडेंट।
These are linearly independent vectors. Why are they linearly independent? Because you cannot obtain one vector by, they are not linearly related to each other. इस केस में अगर आप ये रॉ ऑपरेशंस परफॉर्म करो इस टाइप के, you will never end up with a zero entry, zero column. With the only खाली एक इसमें केस में आप एक जीरो कॉलम ऑब्टेन कर सकते हो, which actually has got no mathematical significance, is when you multiply this by 0 as well as this by 0, which you cannot do actually. Is that clear? तो इसमें कोई भी रो ऑपरेशन परफॉर्म करके या कॉलम ऑपरेशन परफॉर्म करके यू कैन नॉट एंड अप विद द रो ऑफ जीरोस. आर यू गेटिंग मी? इज दैट क्लियर? तो जब भी आपको कुछ वेक्टर्स, अगर आपको एक गिवन सेट ऑफ वेक्टर्स दिए गए हैं v1 v2 सो ऑन अप टू vn, और अगर आपको देखना है कि ये लीनियरली डिपेंडेंट है या इंडिपेंडेंट है, तो आप इन वेक्टर्स की लीनियर कॉम्बिनेशन लो, जैसे मैंने यहां पे ली या यहां पे मैं ले सकता था. आप इन वेक्टर्स की लीनियर कॉम्बिनेशन लो लाइक दिस, अल्फा 1 v1 प्लस अल्फा 2 v2 प्लस सो ऑन प्लस अल्फा n vn. Take its linear combination, put it equal to a zero vector, and prove that these vectors will be linearly independent if the only possible solution of this equation is that all alphas are zero. जो मैं अभी आपको बता रहा था कि अगर ये दो वेक्टर्स हैं v1 और v2, और अगर ये लीनियरली इंडिपेंडेंट है, और अगर मैं इनको कंबाइन करूं आपस में, अल्फा 1 v1 plus alpha 2 v2, I can in no case obtain a vector 0 except if I put both alpha 1 and alpha 2 equal to 0. Are you getting me?
Yes, sir.
Whereas in the case where the vectors are linearly dependent, if I do the same thing, I put alpha 1 v1 plus alpha 2 v2 equal to 0. In this case, you can see here that with alpha 1 equal to 2 and alpha 2 equal to minus 1, I'll be able to get a zero vector. That means I am able to get a zero vector for non-zero values of alpha 1 and alpha 2. Are you getting me? तो ये जनरली आप ये याद रखो कि अगर आपको एक सेट ऑफ वेक्टर्स देखना है कि वो डिपेंडेंट है कि इंडिपेंडेंट है, तो आप एक ऐसी एक्सप्रेशन बनाओ और इसमें प्रूव करो कि ये वेक्टर्स तभी, अगर ये वेक्टर्स लीनियरली इंडिपेंडेंट है, दैट इज पॉसिबल ओनली इफ all alphas are equal to 0. If they are linearly independent, but if there is a non-zero solution of alphas for this equation, then you have to conclude that these set of vectors v1, v2 up to vn are linearly dependent. Is that clear? Is that
Yes.
clear to you?
Yes, sir. Yes.
Okay. तो यहाँ पे भी हम यही लॉजिक यूज करेंगे. हमें ये सेट ऑफ वेक्टर्स जो कि आइगन वेक्टर्स हैं मैट्रिक्स A के, associated with the eigenvalues lambda 1, lambda 2 up to lambda n, I have to prove that these vectors are linearly independent. So what I will do, I will actually take this expression and then go on to prove that this expression is valid only if all alphas are zero. Is valid only if all alphas are zero. That will go on to prove that vectors v1, v2 up to vn are linearly independent. मैंने प्रूव करना है कि आइगन वेक्टर्स मैट्रिक्स A के जो एसोसिएटेड होते हैं with distinct eigenvalues, they are linearly independent. I'll prove them using the same logic. Is that clear? So this you have to remember in general. जब भी आपको कुछ सेट ऑफ वेक्टर्स दिए गए हो और आपको प्रूव करना हो कि ये वेक्टर्स लीनियरली इंडिपेंडेंट है, तो आप एक ऐसी एक्सप्रेशन बना के उसमें ये प्रूव करने की कोशिश करो कि इस पर्टिकुलर इक्वेशन का ये वैलिड होगी ओनली इफ ऑल अल्फास आर जीरो. देन यू कैन से दैट v1, v2 up to vn are linearly independent. In case that's not true, that's not true that you have some solution while some alphas are non-zero, even if one alpha is non-zero. That will go on to prove that this set of vectors is linearly dependent. Is that clear? Clear to all?
Yes, sir.
अब हम इसका प्रूफ लेंगे. प्रूफ के लिए अभी 5 मिनट बचे हैं. It will not be complete, so we'll take it up in the next class. Is that okay? We'll prove
Yes.
it in the next class. That this theorem will prove in the next. This is a very important theorem, and then we will move on to solve some numericals again related to the solution of state transition, evaluation of state transition matrix. और जो हमने कंप्लीट सॉल्यूशन लिया था नॉन होमोजेनियस स्टेट इक्वेशन का, उसकी भी हम कुछ न्यूमेरिकल्स लेंगे. दैट मींस गिवन द इनपुट एज वेल एज द इनिशियल कंडीशंस, हाउ डू वी एक्चुअली सॉल्व फॉर द स्टेट इक्वेशन. इज दैट ओके? एनी क्वेरी और एनी प्रॉब्लम? यस. अगर आपसे क्वेरीज नहीं आ रही हैं तो इसके दो मतलब हो सकते हैं. या तो आपकी समझ में कुछ नहीं आ रहा है या तो आपकी समझ में सब कुछ आ रहा है. तो व्हाट डू आई टेक एज द फीडबैक? And unless you come up with something, I will not be able to do any modifications in my lecture delivery. अगर आपको लगा कहीं पे फास्ट जा रहे हैं, कहीं पे स्लो जा रहे हैं, तो you have to speak up. Is that okay? Is it
Yes,
clear
sir.
what we have discussed so far?
Yes, sir.
तो न्यूमेरिकल्स आप खुद भी ट्राई करो बुक से लेके हम भी ट्यूटोरियल आपको दे देंगे अगला ट्यूटोरियल आपका तैयार हो रहा है so possibly by tomorrow we'll be able to give you another tutorial sheet and once you उसके अलावा भी आप न्यूमेरिकल्स बुक से देख के नेट से देख के आप सॉल्व करो and try to get comfortable with all these things. These are very important things particularly for an electrical engineer from engineering viewpoint as well as preparing for the future career के लिए भी ये बहुत ही important course है. Is that clear? Clear to
Yes,
everybody?
sir. Yes, sir.
Tomorrow is going to be the lab class. So I hope all of you are have prepared your lab reports. So you'll be checking the lab reports tomorrow and also you'll be asked about the previous experiment that we had done in the lab. तो नया एक्सपेरिमेंट भी हम कल दिखाएंगे आपको. So those students who had come last time, I hope all of them will be turning up physically in the campus. और जो बाकी students हैं उनको होता है live streaming will be doing tomorrow. So we'll be doing it through live stream. Okay. Okay. Thank you for today. You can just leave the class and go for the next class.